Good morning. Mr. Matroni will come in a little while to help you with your worksheet. Today I want to give you just a brief introduction to the concept of friction, how it works, and how we're going to solve some problems with it. So our objectives for today, first is to have a conceptual understanding of how friction forces work, and then we'll do some calculations. We'll learn that the friction force depends on the normal force and something else that's called the coefficient of friction. So our agenda is to see how friction works. We'll look at two types of friction called static and kinetic friction. Then we'll draw our well-known free body diagrams using friction. So first off, we observed this in the Poldus lab. If we took that tray and gave it a push, what happened? If you take an object right now, if you take your iPad, gently push it across the surface and let go, what happens? You'll observe that it comes to a stop. Now, why is that happening? If it's changing velocity, that means that there's some force. What kind of force is that? Well, that's the force of friction. So we're going to investigate forces of friction. I'll ask you to do this. We'll pause the video in a little while. I'm going to introduce this PhET, and I want you to explore the PhET activity. So I'm going to have you fire up PhET. Just search for force. You'll see the forces in motion basics, the same PhET that we had worked with previously. If I bring this up, you'll see that there's a friction option. This is what we're going to look at now. So I'm going to bring up friction. You see that here is our figure he can push on a box. Turn on all of the check boxes so we can see all of our options here. So there's a 50 kilogram box sitting on a surface. If we start to push on that box, if I apply 50 newtons of force, you'll see a whole lot of nothing happening. Even though the applied force is 50 newtons, notice there's a friction force pushing back with 50 newtons also. The net force, the sum of the forces, is 0 in that case. If I increase the force a little bit more, then you'll see with 100 newtons, there's still 100 newtons coming back. If we go a little bit higher, now we'll see something curious. It breaks free as it starts to move. The friction force actually drops down. It's going to come down to 94 newtons. We'll talk about that briefly later on. So now the applied force is greater than the friction force. There is a net force to the right. The object is starting to accelerate. You see the speed is very slowly coming up. Cool. All right, let's reset. I'll turn everything on again. Let's make a couple changes. I can increase the mass. Let's try again. I'm going to give a push. I'll apply the 50 newtons, nothing happening. Apply 100 newtons, nothing happening. Even 150, still nothing happening. We have to continue to go higher, higher, higher. I'm going to apply a force of 300 newtons. Now I'm seeing some applied force. I've been able to overcome the friction force. Again, I've got a net force to the right. The crate is indeed accelerating. Notice in this case, it took a lot more force to make it accelerate. The friction force is quite a bit stronger. Why is that? Notice that the mass has increased. That is going to change the force of gravity and the normal force. So we will investigate those things and see how those affect our force of friction. Let's reset here. I'll bring the crate back down. We'll come back down to, I'll just reset everything. I'm going to make one more change here. And notice there's a slider up in the top. We can change the amount of friction. We can make it a very rough surface, lots and lots and lots of friction. I can take it all the way down to where there's no friction at all, where there's just some ice. So if I do this, if I apply just a little bit of force, apply 4 or 5 newtons of force, notice now there's 0 force of friction coming back. So all my applied force is turning into net force. If I increase the friction, now suddenly I'm getting a large friction force. I can make it really strong where it's going to push back harder. It's going to make the box come to a stop. So if we change the property of the surface, see, I'm making the surface rougher here. Now it can increase the amount of friction. Now I have to apply a lot of force to get this guy to work. I have to push really hard to overcome the friction. So that says there's another thing that comes into play here. The stickiness between the two surfaces, between the box and the surface underneath it, will affect the force of friction. So pause the video now, take a few moments. I want you to explore, try different amounts of mass, try different amounts of friction, see how those things affect the force of friction. And then we'll come back and discuss this in a little more detail. So take about 5 minutes and then let's come back in. Okay, so now as we approach this more formally, you see in your book, the chapter 5.2, there's a couple of figures here that show this in a great deal of detail. Figure 7 will show exactly what's going on here. Any object sitting on a surface will have two forces. As we have seen throughout, we have force of gravity, the downward force, we'll have the normal force going upward. For all of our cases, we're going to look at flat surfaces where the normal force is going to be equal to the weight force, be equal and opposite the weight force. Now, anytime you apply a force, you see here we can see I've applied a force. I've got a force. In this case, I've got a force going to the. Here we're applying a force going to the left. You'll see that there's a static force. This is a force of friction going toward the right. Here we're pushing just hard enough we're not having it move. If I push harder, you'll see the force of friction gets harder. It's coming in the opposite direction. The force of friction is balancing out the applied force. We have no movement in this case. So for this situation, we could say the force of friction is, and I'm going to make a correction here, it's actually less than or equal to this thing that we call this Greek letter mu sub s. This is the coefficient of friction. And we have the normal force, just like before. So the force of friction, it can be less than or equal to these quantities. As long as we're not pushing too hard, the box is not going to move, so it will be static. If we push harder, then the object could break free. If the applied force, if the pushing force now is greater than the force of friction, and we'll call this force of kinetic friction in this case, now, if it's greater, we're going to have acceleration. Our net force, just like before, is going to be the sum of the forces. In this case, it's going to be the applied force, or the push, minus the force of friction. If the two are equal to each other, net force is 0. That says we'd have constant velocity. We saw this in the pull this lab. When I pulled the tray just hard enough to have it go at a constant velocity, the pulling force was just equal to the force of friction. If you pull harder, and we also saw that, then the applied force minus force of friction is greater than 0. F net is greater than 0. And then we have non-zero acceleration. Cool. So here's all the pieces now. We've seen that the force of friction depends on the normal force. It depends on how sticky the two surfaces are, that thing we call the coefficient of friction, or this mu k. It also depends on the strength of the normal force. If an object is heavier, or if you're pushing down on it, there will be more normal force. That will increase the force of friction. So both those things can change the amount of the friction. At this point, I'm going to have you start work on worksheet 5.2. So I'll have you pause the video for a second, then we'll come back and we'll look at the first problem. Mr. Matroni will come in a little bit to give you some additional assistance. Let's take a quick look at the first problem on this worksheet. Notice here you're pulling on a 70 kilogram block, pulling on a horizontal surface. Key thing to see is that it's being pulled at a constant velocity. We've talked about this a lot already. What does that mean? You need to figure that out. So the coefficient of friction, we're giving you this number now. For this case, the kinetic and static coefficient of friction are going to be the same. There's a number of 0.78. Notice there's no units with the coefficient of friction. It's a dimensionless quantity. So first thing I want you to do is draw the free body diagram. We have four forces at work here. Force of gravity, normal force, the pulling force going to the right. Force of friction is always going to oppose the way that you're trying to move it. Next, you're going to write Newton's second law. Just write it that the net force is going to be equal to mass times acceleration. Notice here we're focusing on the y direction. We're now working in two dimensions. We're going to be working up, down, and sideways. So you see this block is not flying off into space or dropping through the floor. So the acceleration in the y direction is going to be equal to 0. That tells us our net force in the y direction is equal to 0. Therefore, we can find the normal force. Net force is 0. That tells us that normal force is going to be equal to force of gravity. Go ahead and calculate that. I'll let you figure out that. Once you've got the normal force, then you can find the force of friction. Force of friction is just going to be equal to the coefficient times the normal force. So work out all those things, figure out what that is, and finally, you're going to figure out how hard do you have to pull on this block. How hard would to pull just to overcome this force of friction? We have to balance it out. We're going to have a net force in the x direction. What is the net force going to be if we're moving at constant velocity? Figure that out. Figure out what the force of friction is. Okay, at this point, I will leave you to work on the worksheet. Mr. Matroni will be in a while to help you through it. If you have questions, I would say ask him any questions that you got. I'll be back in here on Monday. I'll catch up with you then. Thank you very much.